Hello everyone, welcome back to Calculus 1. And this time we are working on section 4.6, limits again. And this time we are going to consider a special kind of limit at infinity. So first I do have some simple facts about limit at infinity. Consider 1 over x. As x approaching to infinity, it is 0, right? It is in the situation numerator is 1, denominator keeps growing, keeps getting bigger and bigger. So the limit should be 0. Okay, and similarly, limit as x approaching to infinity, 1 over x squared is still approaching to 0. And indeed, we could get this thing in a more generalized result. Limit as 1 over x to the power n. As long as this n is positive, this n should be positive. 1 over x to the power of n, it is just 0. Okay. And also, speaking of infinity, another kind of infinity is the opposite direction, getting smaller and smaller. We write the situation as x to the negative infinity. So as x approaching to negative infinity, 1 over x, you may want to say, this time the result should be negative, right? But anyway, you will see, even it is negative, but anyway, those values are really getting closer and closer. It is approaching to 0. 1 over x squared still it is approaching to 0. And the 1 over x to the n is still approaching to 0. So in general, it really doesn't matter x approaching to infinity or negative infinity. Sometimes we write them together. 1 over x to the n simply it is approaching to 0 for any positive number of n, any positive power of n. Okay. And also another interesting fact here is I said all the cases, okay, limit at infinity, numerator is 1. Then you may wonder what happens if numerator 2 or numerator 10. So I got some little big numbers here on my notes. Numerator is 100. You think it very carefully. Let's just consider limit of 100 over x, okay? And then you will want to know x approaching to infinity. It is bigger than anything you could imagine. Okay, well, 100 in any way, 100 is not going to beat infinity at all. So 100 over x, that is approaching to infinity. And also you can try 100 over x squared, 100 over x to the power of 3, those things. They are just all approaching to 0. And also you could count in the case x approaching to negative infinity. This limit is still 0. And similarly, okay, 100 won't work, make it 200. And I just have to tell you, well, 200 still is not going to beat infinity. Okay, so overall, such a limit still it is approaching to 0. And if 200 is not working, how to make it 2000 or 3? I have like 300,000. Or you can make it 3 million, or if you want, you can make it 3 billion. It really doesn't matter what kind of numerator you may have. As long as the numerator is constant, okay, it really will not beat the situation when the denominator keeps getting bigger and bigger. Okay, the denominator is infinity. No number will beat infinity. Infinity, oh, another thing worth to mention, infinity, it is really not a number. It just denotes the situation. It's getting bigger and bigger than anything you could imagine. That's infinity. So not a single number will beat the infinity. So overall, so far, all the limits I talked about really can be summarized into this situation. Limit as x approaches to infinity, positive or negative, of any constant over x to the power of n. It is just 0. It is just to the power of 0. The only restriction here is the constant could be of any number, positive or negative number. The power got to be positive. The power got to be positive. Okay. So how about let's look at some examples. I just took the examples from the textbook directly. This is example 4.51, part A. Limit as x approaching to infinity, 5 minus 2 over x squared. Remember, we do have some limit laws, right? The limit of sum, it is sum of limits. Limit of difference, it is difference of limits. So indeed, the limit of those two expressions, the expression, a single expression, would be considered the difference of two limits. Certainly, as x approaching to infinity, the 5 stays as constant. So I really don't even bother with the notation for this number 5 here. And certainly we will have to consider this limited situation for the second term. But as we just explained, as x keeps getting big, 2 over x, it is really approaching to 0. So this limit, it is 5. Limit, it is 5. For this limit at infinity, it is 5. And also it is worth to mention because so far those results, okay, previously I discussed, they are all for zeros. But you still don't want to say limit at infinity, it is just 0. It could be of anything. Like in this case, it tends to be 5. And also the next case, limit of sine x over x as x approaching to infinity. Okay, I hope you see this limit kind of look familiar. Indeed, I do have a little bit of comment about this kind of limit. Okay, but anyway, let's finish out discussion for the limit at infinity first. Keep in mind, infinity or not, x keeps getting bigger or not. Okay, sine x, it is a periodic function. Sine x always stays between -1 and +1. Because x, it is approaching to infinity, so it's fair to say we can consider x as positive. Okay, so what I'm seeing here is sine x over x, it is between -1 over x and +1 over x. And then, well, if you remember, I'm really talking about the squeeze theorem. What I figured out here is the sine x over x, it is sandwiched in between a lower bound and a lower upper bound. And in this case, not surprisingly, I say, well, the lower bound and the upper bound, they are approaching to the same limit, right? Which really means for anything sandwiched in between, it really has nowhere to go at all. It will have to take the same limit as 0. So this limit, it is 0 because of the squeeze theorem. Okay, without using squeeze theorem, it might be a little harder to track or to be convinced. And then if you are fine with this limit, as I said earlier, this limit doesn't look very familiar to me because in the very beginning of the semester, we did talk about a limit like this. But anyway, it's not the limit at infinity. It is the limit of sine x over x as x approaching to 0. And I hope you remember this limit, it is 1. And indeed, we are going to look at this limit again. Okay, we are going to look at this limit again at least there's one more time. Probably will be in a week or two. You will see this limit again. And when we talk about the L'Hopital rule to find out limits. Okay. This is part B. Maybe let's give a try to see finish this part C before we take a break. Part C, what we are looking for here is the limit as x approaching to infinity tangent inverse of x. So indeed, I want to say, mostly, even including me, I have been teaching calculus for many years, but anyway, I really don't feel very comfortable to talk about tangent inverse. So what I did, instead of considering tangent inverse directly, let's consider tangent. Tangent, it is a periodic function between -π/2 and +π/2. Okay. As x for tangent, okay, this part, for tangent, as x approaches to π/2, tangent value, it is approaching to infinity. And then think about the inverse case, and also the book does provide very nice graph for the tangent inverse. I just copy and pasted from the book for the graph of tangent inverse here, okay. Basically, it simply says as x approaching to infinity, tangent inverse, it is approaching to π/2. So this is The result I provided, limit as x approaching to infinity, tangent inverse of x, it is pi over 2. So this is the first part of limit at infinity in section 4.6. Thank you for watching. See you next time.